I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. I just ask that you bless this class today, Lord. In your name I pray. Amen. So as you guys are well aware, we are trying to find a solution to the fact that my PDF is sadly too dim. This is the solution we came up with. So here it goes. So we're talking about a connection. Well, we talked about principal fiber bundle last time, which is a fiber bundle where the typical fiber is a group, and there's a natural group action on each fiber. And so if we have a section of the fiber bundle over the base space, that basically gives us a local attachment of a gauge element, a group element, in a continuous fashion over the manifold. But then we can look at these things called connections, which have to do with, well, connecting different tangent vectors in the total space to the bundle. So here, this is the tangent space to the bundle. And so basically, the point is it's the Cartesian product of the tangent bundle to the base space and the tangent space to the fiber. But the cool thing is, there are two pieces we can basically view as horizontal, and man, I wish I could find my glasses. It's just fuzzy to me. I'm just guessing. I can see it clear over here, but anyway, there's a horizontal space and a vertical space. And we have these bundle maps. Ah! Curses. Oh no, what have I done? Oh no. Sorry. Curse the cursor. Goodness gracious. All right, well, that was a little bit ahead. Anyway, so vertical vectors are for free, but the horizontal vectors need a choice, and that's what the connection's about. So we'll try to explain that as we go on here. So a connection splits the tangent space at each point in a systematic manner. So we got to pick a horizontal piece and a vertical piece. So we can decompose at the point level, but the vector level or higher, we need some sort of natural definition for vertical vectors. That's given to us in terms of the projection map, which comes for free in the fiber bundle. So here it is. Here's the definition of vertical. We have a fiber bundle for a vector to the tangent, a vector in the tangent space to the total space here. It's vertical if and only if the push forward under the pi is 0. So that means, in some sense, that the tangent vector lines up with the fiber. We could kind of think of it that way. That's why we call it vertical. Where, of course, the differential of the projection map maps from the tangent space to the total space to the tangent space of the base manifold M. And we denote the set of all vertical vectors by VTE, which I have no particular pun for. Sorry, Jess. Okay. You'll find a pun. I don't doubt that. So if we have an open set, then the projection from U cross F to U is a canonical projection. We actually have the following formulas, like the differential of the pi U map. It's really just an honest to goodness projection on those pairs of tangent vectors. It just picks off the first part. So this is sort of the naive thing that this concept's trying to generalize. It's not always so simple as this, but in the case you have a trivial bundle, the d pi is really just a projection, right? It's a projection onto the part of the tangent vector which lines up with the base tangent. So it just kills off the fiber piece. Or is it the opposite way around? Exactly the opposite way around. It keeps the piece which is tangent to the manifold, that's the Vx, and it kills off the Wf, which is the part which is tangent to the fiber. All right, anyway. So there's what vertical means. Ah! Come on. I'll get it eventually, guys. So for example, let's see here, I'm going to move around a little bit. So here we have R3 with the origin removed. We can look at this vector field, ABC, the radial piece and the angular pieces. And we look at the bundle R plus, the Cartesian product of the positive reals with the two sphere. So this is a fiber bundle with fiber S2. It's a trivial bundle with fiber S2, where the projection map just gives us the radius part of P. The horizontal, so in this vector, let's see here, what's dP do? It sends this piece to 0 and it just keeps that piece. All right, that's what the push forward under the pi map does. It just kills off these two guys. So in any linear combination of the angular derivations is 0, whereas, well, in fact, d pi is dr in this case, so in this notation. All right, anyway. I'm not sure how much of these details we need to get into. I'll try to go over a little bit so we're not too lost as we go on. So proposition, using a local trivializing map for an arbitrary fiber bundle. So in other words, remember, it's that map from the inverse image over the base space to the Cartesian product of U and F. We can claim that V is a vertical vector if and only if it is the tangent to the fiber of E through U. Tangent to the fiber of E through U. Oh, okay, so the fiber is a particular submanifold of the total space, right? That's like a submanifold, so it makes sense to talk about whether or not, V is tangent to that fiber, right? Which I kind of picture like this. So it's a vertical vector if and only if it's tangent to the fiber. That makes a lot of sense, actually, if you think about it. All right, but there's the details. All right, so the next few pages are devoted to subbundles, which I don't think matter to us. So I'm going to skip past this subbundle stuff. Here we go. So here's what a connection is. A connection on the fiber bundle, EM pi F, is a subbundle. Sadness. Well, maybe we can figure it out. It's a subbundle H of the tangent bundle such that for every U and E, the tangent space to U at E is HU direct sum with the vertical piece. So I think you can guess what a subbundle is, right? It's going to be fine. Curses. Thought I got away with it. So let's see here. If H to Q is a vector bundle, then a bundle K to Q is a subbundle of H, if and only if KQ is a subspace of H, Q for all Q, or it's required that for every Q in Q there exist local sections from U to K, from K to Q, such that this is the basis of K for each. So you've got K basically appears in an inclusion inside H, and the inclusion BAP is the vector bundle isomorphism. Well, that's a subbundle of a vector bundle, but is that what we have? I mean, a principal fiber bundle is not a vector bundle, so what does that matter? Oh, but this is a vector bundle. Why? Is it a subbundle of E? No, it's a subbundle of what? TE. There's got to be something there for you, Jess. TE? No. TE phone home. All right. Fine, I'll accept it. Anyway, the point is that is a vector bundle, so saying subbundle in the sense that I just glossed over makes sense. The larger point is that this subbundle picks out a complementary subspace to the vertical space in the sense that I was looking at a second ago, but now I've lost track of. Dang it. What this is saying is that the vertical tangents form a subbundle, all right? That's not the, I had gone a page ahead of this, which is to say that, so the vertical tangents form a subbundle of the total tangent space to the fiber bundle, to E. But then a connection is yet another subbundle. It's in subbundle H of the tangent bundle TE, such that at each point in the total space, we can break up the tangent vectors to the total space into a horizontal part and a vertical part. That's one way we can define connection on a principal fiber bundle. So the kernel of the push forward of pi, or the kernel of the differential of pi, if you like, that is the vertical tangent space at U. Let's see here. On the other hand, if we were to restrict the differential at pi to the horizontal tangent space, well, that's a one-to-one map, because the only vector which is vertical in the horizontal space is what? It's the zero vector itself, because this is a direct sum decomposition, point-wise, for each U in E. All right. So that's a vector space isomorphism, in fact. You know, this is kind of important. You can think of the horizontal space in some sense as being the tangent space to the base manifold. The dimensions work out that way. And in fact, it's a vector space isomorphism, and you can think about lifting. So if I've got a vector field, on the base manifold, I can lift it up to the total space E. Well, that, you know, according to this rule, I just take the inverse image under the differential pi, and that gives me a new vector field x tilde up on E. So this allows us to lift vector fields on the base space to vector fields on the total space. Again, a recap. Vertical vectors lie in the tangent to the fibers. We've got this non-singular d pi restricted to the horizontal space. It's an injection. The dimension of the vertical piece of the tangent space is the dimension of the fiber. The dimension of the tangent space at E is the same as the dimension of the base space across the typical fiber, which in this case is a group, actually. I don't know why we're not saying G everywhere. I guess this is because, oh, you know what it is? I keep saying we're looking at the connection on a principal fiber bundle, but that's not the case. Actually, this is describing the connection on a fiber bundle. I kept saying F is equal to G, but nowhere in these notes is it said. And that's because what we're defining is the connection on a much more general fiber bundle. We don't have to have F equals to G. All right? I put that in there. That's not there. So, I'm sorry, King. I know this is rough. Let's see here. Where are we? So anyway, the point is that the dimension of the fiber bundle is the dimension of the base space plus the dimension of the fiber. And so that is how we knew that the dimension of the horizontal space is, in fact, equal to the dimension of the base space. All right, anyway. So this approach is algebraically clear, but pragmatically, we can employ differential forms for a connection, which is the next connection we'll make. There you go, Jess. There's one right there. So on September 13th of 2005, when I took this course, we defined an Ehresmann connection. I say we, I really mean Dr. Fulp. Anyway, so the Ehresmann connection is a mapping from the tangent space at U to the total space to the vertical vectors. All right, and it's just defined by projection of this onto the vertical piece. That makes sense because, I mean, why? Because the connection, if we're given one, tells us we can select a vertical and a horizontal piece for each tangent vector to E. So this is just taking advantage of that. We basically feed gamma a vector up here, and it spits back the horizontal piece. So it kills off the vertical piece, all right? Like it says here, the kernel, oh, I'm got it exactly backwards, I'm sorry. The kernel of this is the horizontal piece, so it kills the horizontal piece, right? And it just maintains the vertical piece, I suppose. Like all projections, it's, if you do it twice, you get back where you started again. Let's see here. So this provides an alternative way of splitting the tangent bundle at E. Namely, we can define a connection by giving a smooth mapping gamma from the total space to the vertical space smoothly, such that it squares to itself. And if we take gamma u restricted to gamma u of the tangent, we get the identity. Anyway, so we can, in this view, we can then define the subbundle from this map as the kernel of the map at a point. So like you can either start with the subbundle and construct the map, or you can start with the map and construct the subbundle. These are just two different ways of capturing what a connection is. All right. All right, now, finally, what I was wanting to talk about from the start, I keep talking about principal connections. So suppose we have a principal fiber bundle, and you want to talk about a connection on a principal fiber bundle. That would be, of course, a principal connection. So we've got P, M, pi, G. In other words, the fiber is a Lie group. In this case, if we have zeta, an element of frac G, this is the Lie algebra, and we define a vector field, squiggle number, on P. I mean, what do you want to call this? Snake number? It seems like snake number, maybe. What's that? Hiss number. Anyway, this thing on P is defined to be the derivative of this curve at 0. So what is this curve? We're exponentiating the Lie algebra. This gives us a Lie group element. And this right here is something in the fiber multiplying in the group element. This is a curve in the fiber, and it's going up and down the fiber. So it's actually a curve along one of the fibers. We're differentiating it, setting time equal to 0. So it's giving us a tangent to a curve which is lining up with one of the fibers. And so that's a vertical vector. I'm sorry, King. This is not nice. Like this is some form of unnatural mathematical torture at the moment. Let's see. Yeah. Let's see here. I need better eyes to read this. We use delta in the fiber bundle notes, and Kobayashi uses unknown symbol for this. Notice here, exponential is in the Lie group. U acts on the left of the group and implicit within this principal fiber bundle. And note that sigma sub u is a mapping from the Lie group to the principal bundle defined by that. All right. This is everything I was just saying, is that this map that we're differentiating is set equal to 0. It's a curve that lies along the fiber, which, by the way, is the group. And so the derivative to that curve is a vertical tangent vector, but it's also a Lie algebra element. So that's the thing here. So this is defined to be that, which we can do the calculation, is this, which is that. So the differential at the identity of this sigma u acting on snake, so it should be obvious that this is linear in sigma, rather in snake, if we fix the u, all right? And what more so here's a picture. Here's a picture of what's going on. So think of this square as being the Lie group, all right? And this is a curve. This is the curve as t varies. We're along this curve in the fiber. And then that's the tangent to the curve, which we're calculating right here. And so anyway, the larger point here is if we calculate the differential, the push forward of that thing under pi, we get this, which gives us that. But remember that pi composed of sigma of u is just constant. It's pi of u along the whole fiber. That all evaluates to the same point. So when you differentiate that constant map, you get 0, which is to say that the push forward of that is 0, which is to say that that is indeed a vertical vector, as I was just telling you. And so, in fact, we have a mapping from the Lie algebra G to the vertical tangent space, to the principal fiber bundle, which is to say that there's a one-to-one correspondence between the Lie algebra and the vertical tangents at a point to the principal fiber bundle. And so this is the mapping from frac G to that, defined by squiggle, maps under this map to squiggle sub u number. That's an isomorphism of vector spaces. And so we have a copy of the Lie algebra, which is naturally identified with the vertical tangent vectors at a point, which is pretty cool. And so this is in fact a vertical vector field, all right? But anyway, not every vertical vector field is of that form, blah, blah, blah. Okay, proof. I definitely don't want to look at that at the moment. on here. So definition. So we got about a half hour left, right? Definition, we have the principal bundle, the base space, the projection, the Lie group, a connection from H to P. We could say it's a subbundle. It's a principal connection if and only if we have the following. So it's a little bit more. There's a little bit more fine print for it to be a principal connection on a principal fiber bundle. We want, yes, it's a subbundle. That would be enough in the abstract fiber bundle context. But we want more. We want it to behave nicely with the group action. For G and G, we want the differential of the right action of G on the HU to be H of UG. So, give us a... So is there something you want to say, Jess? Do you have something to say here? What's that?
No comment.
You have no comment?
I can't be forced speaks for itself.
Okay. Okay. I thought you might want to hug. But anyway, where RG goes from P to P, there's a right translation. This is the right translation. It's fine. Anyway, so here's the picture from the subbundle to the tangent space to the P, back to P again. All right, anyway, I'm not getting a lot out of this. Let me go on here. If I can find my button. All right, so we can prove that drg acting on the vertical part of the tangent vectors to the principal bundle is the vertical part. So this is, all right, so what is this? This is the right, stink, curses. Well, anyway, you need to get into the Lie groups and the Lie algebras to really appreciate this, is all I can say at the moment. All right, guys, I mean, I'm trying to summarize a lot of stuff here in a pretty short time. At some point, some details I've got to give, and this is going to be one of them. All right, so moving along, trying to get some big picture here for you. Come on. All right, so starting again, new day. New day has dawned. So given a principal connection on a principal fiber bundle, one has a corresponding Erasmus connection, gamma from TP to VTP. And one also has, for each U, an isomorphism from the Lie algebra to the vertical tangent vectors over a point, given by this map. And we can let sigma U be the inverse of this map, and that will give us a mapping from the tangent space of P to the Lie algebra. Aha! A mapping from the tangent space of P to the Lie algebra. This is nothing more than a Lie algebra valued one form on the tangent bundle. Now that's kind of neat. If we fix a point, then we've just got a Lie algebra element. And with here, omega sub u is phi sub u composed with gamma sub u. And here's the story. And the following properties they have. So the connection form omega u acting on a horizontal tangent vector gives us 0. The connection form acting on a vertical vector, this thing gives us back gamma again. So the horizontal piece is like in the kernel of this one form. So we can look at a one form and look at its kernel to pick out the horizontal piece. It's kind of neat. And it turns out, as he says, it's not immediately obvious, but if we take the connection one form omega and act on the the differential of the right multiplication by G map acting on this vector field, well, that's the same as calculating the adjoint of G inverse acting on this. What is this adjoint map? Well, it's defined down here. The adjoint of G is the differential at the identity of IG, where IG is the conjugation map in his notation. So this is actually the differential of the conjugation map. There's a lot going on here, right? I mean, we take the group conjugation, differentiate that thing at the identity. That's this map. All right. Not immediately obvious. Yeah. My guess is we'll probably calculate that here in a page or two. But let's see here. So this is the lemma. So we're working on calculating the boxed thing. So the differential UG of snake number sub u is the adjoint G inverse of snake, the number of that at UG. Oh, what a monstrous formula. So omega u, let's see here, what's this picture? We're going from this to that. What's going on here? Omega u is a mapping from what? From, what did we say? It was mapping from TP to the vertical space? What was it? I've already forgot. Oh, here it is. It's a mapping from TP to G. If we, omega sub u, though, is a mapping from, what's that? Tu of P, right, to G. Yeah. Let's see here. So the horizontal space is the kernel. The range of it is basically filling out vertical vectors. Well, I shouldn't say the range, I'm sorry. And that formula. All right. Let's see here. So anyway, I think to really, I mean, it would take us, I think it would take me a solid, like, complete lecture, full hour lecture to really prove that formula carefully, piece by piece. Maybe longer. I mean, we'd have to build up all of these different maps that we're talking about and understand Lie groups and the algebras and how they interplay. You know, there's a lot to do here to really understand all the moving pieces. Yeah, I mean, you can do Lie groups in the algebras. If we have a semester course, we could do it, yeah. Supposing we already had manifold theory, which, of course, would then properly suppose we already had topology, which would then properly suppose that we had a real course in real analysis before that. I mean, there gets to be a link.
What are you saying about real analysis?
I'm saying that most U.S. universities can't teach real analysis anymore. So anyway. Okay, anyway, so if we have two principal connections, omega 1 and omega 2, then the difference of them has certain properties, like tau sub u is 0, that's 0. But look at this. The difference under the pullback of right multiplication by g of tau is actually the adjoint of g inverse of tau. So that's kind of funny. If you look at that, what that means then, right, is that the difference between two connections is somehow related to, in some sense, this animal. So people say that a mapping satisfying conditions 1, 2, and 3 here is a pseudo-tensorial thing. For example, this is a pseudo-tensor. These are the Christoffel symbols. So Christoffel symbols don't transform as a tensor. Okay, anyway, the larger point here is that maps like tau are in one-to-one correspondence with sections of the bundle. This is the Lie algebra bundle. So if we were to take, and this goes back to that associated bundle idea that I glossed over. So this is the associated bundle. What this is implicitting, we take the Cartesian product modulo some relation that's based on the Lie algebra action. That little g means something somewhat technical. But the point is that there is a one-to-one correspondence between those mappings tau and sections of this corresponding bundle. And g acts on the adjoint representation like so by that adjoint map. All right, I'm sorry, it's getting a little thick. Jet bundles. Ooh, jet bundles are neat, but we must go on. Should I talk about jet bundles? I I mean, you know that thing we do in differential equations where we introduce variables to reduce order? Like we take an nth order problem and we convert it into a bunch of first order problems through like we say, oh, if you got y prime prime and y prime and y, we'll just say like y is equal to x1, x2 is equal to y prime, x3 is equal to y prime prime. That kind of idea, introducing variables to get rid of derivatives formally. Chasing that idea down in the abstract is what leads you to jet spaces. Jet space is some sort of larger space where you can treat derivatives on the base space as if they're independent variables. And also for fields. But anyway, there's tons of stuff to learn there. Okay, so we talked a little bit in my first very bad lecture for the semester. I talked to you about the physics of this, right? Namely that you can build a Lie algebra valued one form from you got your functions on the base space, and this is an algebra index, and this is a space-time index, and there's an Einstein summation going on over both of them. So, I mean, we have a Lie algebra valued one form, but the difference here between the omega I was just talking about is a one form on the tangent bundle. So it's a function of like p, right? The u is a point up on the total space on the fiber bundle, p, the principal fiber bundle. Here, a is a function of x, which would be like pi of u. The coefficients of a here are functions on the base space. So it's kind of similar to the omega, but it's not, because this is a function that where these a's are function of is different than what we were just talking about. So related, yes, but not quite the same.
Are you saying big A or little a?
I'm saying the big A is like the omega in some sense, but not. The little a, this is just the components of big A. I mean, this is a Lie algebra valued one form. But the point is, it's a Lie algebra valued one form on the base space. The omega we were just talking about was a Lie algebra valued one form on the total space on the p up on the fiber bundle. So next time, which is this time, we will. Well, here's the summary of what we're about to do. The pullback under a section of the Lie algebra valued one form on the fiber bundle is that A we talked about in physics. The pullback under another section is another Lie algebra valued one form on the base space, A bar. And on the other hand, if you had two different sections, right? Two different sections on the principal fiber bundle, they're related by multiplication by a group element fiber-wise. The question is then, how does A and A bar relate on the base space? So here's the picture again. So we have a principal fiber bundle, P, M, pi, G, and we have a fixed left action of the Lie group on the V, which acts linearly on the finite dimensional vector space V. All right, great. Oh, phooey. Now I'm talking about how the principal fiber bundle acts on functions which take their values in some, this would be like a wave function or something. It takes its values in a vector space V, which represents some symmetry in physics. Well, this is how the principal fiber bundle interacts with such fields, in particular by this formula. This is not what I wanted to do. Hey. Aye. All right. Fine. No, I have to skip past this, guys. Whoa. That's some gory details right there. All right, so we're about to get to the thing I wanted to see, and then we took this long detour into discussion of equivariant maps, which is interesting and important to physics as well, but just not where I'm trying to go today. Now he's building the covariant derivative on functions that have to do with a principal fiber bundle. Oh, come on! Hey, when are we going to get back to it? Ay, ay, ay. I will eventually get to it, guys. I'm sorry. Where'd it go? Yowzers. All right, I must have skipped past it. All right. Sorry, guys. Let me come. All right. This next time little blurb here was very seductive, but it doesn't seem to be. I guess I have to pay the price. All right. So we have a fixed. All right, fine. So he wants to define equivariance of a map from the principal bundle to a vector space. And so what does it mean for a mapping to be equivariant? It means that if you vary along the fiber in the bundle, right, like that, then you can pull a G inverse out for the map. This is some sort of like condition to play nicely with the group action fiber-wise on the bundle. This is equivariance. This is a little bit surprising, but that has to do with the choice of conventions, left versus right and so forth. Anyway, so this has to be true for all U in the principal bundle and for all G in the group. And it says the inverse is just because we have left and right actions, thanks to thanks to linear algebra. Yeah, we pretty much multiply stuff on the left in linear algebra, right? I mean, correct? So here's a picture of what's going on. This is the equivariance. Here's U, here's UG. Phi hat moves from P over here to this vector space. The vector space is just whatever that also allows an action of the group. So the group could be, for example, GLN. And then the vector space could be Rn. And we're just talking about matrix multiplication of GLN on Rn, right? If we had a principal fiber bundle which had principal gauge group GLN, for example, the frame bundle. But anyway, so this is the equivariance, is that if I do U, map up here to U dot G, then that's the same as if I go over here and, you know, do G inverse dot phi of U. So phi of U maps over to here. So anyway, note that for U and the P, there's a mapping U hat, which goes from here to here. What was the question? Oh. Sorry, I was trying to not get into this, but I guess I have to. So theorem, there's a one-to-one correspondence between the set of equivariant maps from the principal bundle to a vector space and the set of all sections of the vector bundle, the associated vector bundle to the principal bundle under this pi tilde map. Explicitly, the given equivariant, given an equivariant map, phi hat from P, the corresponding section satisfying the condition is this. So we can take the equivariant map and we can convert to a section of, I guess, this thing, like so. Lost my coffee hole. Where'd it go? There. All right. And on the other hand, if we're given a section, we can create an equivariant map. So this correspondence is really a vector space isomorphism. These are vector space structures hiding here, blah, blah, blah. Recall gamma from last course. So do you guys remember gamma from the last course? Remember when we had general relativity, or Riemannian geometry before this? No, it's completely inappropriate for me to be showing you these slides. I understand that. So you'll forgive me, but every once in a while I got to be crazy. So here we are. I know what this says about you. But let's see here. You're here. Sorry, I should stop insulting you. But what's that? Tim. We named the vector bundle Tim. That is the kind of, yeah, that's, okay, all right, I'll take it. So of course this is a 1-1 bundle. This is a section of things built from the tensor product of differentials and partials like that, and so it's a type 1-1 tensor. I can't be wrong, whatever system of notation I'm using, whether the type PQ means type QP or vice versa, 1-1, I can't be wrong. So if you've forgotten what type PQ means, you're still right if you talk about a type 1-1 tensor. Woohoo! Anyway, stupid comments aside, T hat from the frame bundle, let's see here. We want to get rid of the charts and use RM. So I think what I'm trying to do right now is to describe how the frame bundle acts on this bundle. So what this page is about is explaining that construction of the associated bundle construction playing out in the specific context of the principal fiber bundle being the frame bundle, and it's acting on the vector bundle T11M. And this is what it looks like. And it's just really a fancy way of producing the usual coordinate change formulas on a basis. All right. So motivation, differentiation can be done in two ways. And covariant derivatives on a section has nice geometry, whereas in physical theories, the group G look at the frame bundle into the OM. It's the orthogonal bundle, which is a subbundle of the frame bundle. That's a reduction. I'm not sure that's actually a subbundle. It's kind of a reduced bundle. These have the same base space, but this has a different group. This has orthogonal group as a fiber. This has the general linear group as a fiber. So it's not exactly a subbundle. It's something different. It's a reduction.
Can you go back to this? G is the metric we're talking about, right? Is G a metric here?
Yeah, that's the metric. Yeah.
So just X.
Well, actually, no. I think this G here is not the metric. G is a. This is an invertible. This is an invertible n by n matrix, and it could be. Yeah. I guess it could be, but that'd be weird. I think so. Yeah. Let's see here. So oh, goodness gracious. Yeah. Sorry, guys, I'm looking for something. I found it last time. Goodness gracious. Well, in any event, this is worth looking at for a second. So the covariant derivative of an equivariant map, it's the exterior derivative plus the connection one form dotted with the hat, where this has a specific technical meaning. the action of the algebra valued one form on the equivariant map like that. And when you get into components, it's quite interesting, that's where you see the A's, like we talked about in the physics day, come out to play. Let's see here. So here's a metric tensor. So yeah, if we look at the covariant derivative, oh, we got stuck. Curses. All right. Here we go. Finally, back to the main event here. So if we have principal fiber bundle, a linear action of the group on a vector space, we're thinking about this as maybe being, they could be vectors, they could be one forms, they could be, whatever your favorite kind of object that you're looking at is. And you get a section of the associated bundle. This is, again, a way of, building vectors or forms or tensors of whatever particular type at each point over the manifold, gluing them together smoothly, and then allowing for the principal, then allowing for the gauge group to act on those things locally. That's what this whole thing is doing. Then this corresponding equivariant map phi hat, meaning this, the covariant derivative of phi along a vector field x, is the section of this thing defined as follows. So covariant derivative of the phi map in the x direction at x is the, and this is one of those lifts of the vector field up to the total space, like I was talking about earlier. Oh, maybe here's a picture. I know, I fine guys, I'll admit it takes a while to really, really understand these things, but they're very interesting, I think. So this works for any bundle where you have any action of any sort of equation. For example, SU3 and QCDX on complex 3 space, that would be your vector space. You take a principal fiber bundle with group SU3 and connections and so forth. Theorem. So suppose we have, all right, great. So here's what it actually looks like in components, the covariant derivative I was just talking about. So the pullback of that connection one form under a section, the components of the pullback are the A's that we talked about in physics. And so when you actually look at the formula for the pullback, formula for the covariant derivative, these A's, the pullbacks of the connection one form I was talking about, those appear as sort of the modification. So you have the derivative piece, like that's not surprising. And then this piece is surprising. That's the part of the covariant derivative which has to do with the influence of the gauge group on the geometry. And so here's a summary of what I just said again. So this is the formula for the covariant derivative. And when you actually get it down into components, it looks like this, where these are the, again, the algebra valued one forms on the base space. You should have a formula comparing those in two different systems of coordinates soon here, if I just don't miss it. Come on. I mean, it might have to go back to that. It was like 20 slides ago, but I looked at that tau map with the difference of the sections and how they're related. Surely we've written them again here somewhere. Come on, write it out. Or maybe it's in here somewhere. I see it now. He talked about the tau map with the two different connections. He took the difference of them. He showed that the pullback of the difference was related to the adjoint map. If you put that together, what we just looked at, then you get the formula for A versus A bar on the base space that I wrote down on the physics day. Next up, the curvature of the connection. What is that? Well, if you take the connection one form, omega, and you take its exterior derivative, and you evaluate that sucker at the horizontal parts of the vectors x and y, this is by definition the curvature 2 form at the point u acting on x, y. All right, and that's also the covariant derivative of the connection 1 form by definition. So proposition, if omega is a principal connection, then omega u is this, oh, and it's also calculatable as this, the ordinary garden variety exterior derivative plus the Lie bracket of the connection 1 form with itself like that. And that's where that really cool field strength formula I showed you guys in the physics day came from. Maybe I'm dancing all around the formula I want. Ah, killing me. Write it down. Write it down. Well, this is another interesting formula. So the covariant derivative of the connection 1 form, it's the exterior derivative of the connection 1 form, plus 1/2. These are the structure constants of the Lie algebra. And then omega b wedge omega c, like that. So if you look at this in if you pull this back to the base space, what you get over here is the field strength. This is the derivative of the connection 1 form on the base space A, plus, like, this is the AA term in the Yang-Mills field strength. We get that extra term over there. In electromagnetism, we only get that piece because there is no, well, the gauge group, the structure constants are 0 when the gauge group is U1 because it's an abelian group. Come on, will I ever write the formulas? Yes, this is general and great. Not what I want. Oh, there's one. So explicitly what I was just talking about, we pull back under a section, and that will give us the pullback of S star d omega as d star, like that, which is to say that the pullback of the exterior derivative is the exterior derivative of the pullback, and that gives us this formula right here. Because we're defining A to be the pullback of omega, which would be wonderful if I wrote it somewhere. So A is the pullback under S of omega. Why is that not written anywhere? Sorry. It's driving me nuts. Yeah. So finally, in summary, in the principal fiber bundle, theory of principal fiber bundles, we study a principal curvature. The principal curvature is the exterior derivative of omega plus omega wedge omega in the proper system of notation. The pullback of this is the field strength is equal to the exterior derivative of A plus A wedge A. Or, and sometimes physicists speak, dA plus A squared. Where you're supposed to know that this is the Lie bracket of A with itself, because A is a Lie algebra valued 1 form. And here's the cool thing. Under principal fiber bundle, if you study coordinate change, like if I was to say, pull back under Rg of omega, I just get this relation here. And, oh, come on. Would I really? Oh, man. Well, bummer. I thought I actually come out and said the actual, oh, goodness. Now this is challenging. All right. Whee! I have to admit, the formulas I want to be here are just not here. I thought they were here, but I think I thought I saw what I wanted to see and not what's actually written. Well, I hope we've all learned an important lesson. Don't let Dr. Cook read his notes. Actually, all right, I'll stop. So if you want to turn the lights back on here, you don't have to stop it just yet.